Hello, this will be a demonstration of proposition 332 from book 3 of Euclid's Elements, which states that if a straight line touch a circle and from the point of tangency there be drawn across in the circle a straight line cutting the circle, the angle that it makes with the tangent will equal the angle in its alternate segment. What this looks like is that we have some circle A, B, C, D, like so. It's about a circle. And we have the straight line EF touching it at the point B, like so. And we have some arbitrary points here. We have A, we call that D, and we'll call that C. And we have the straight line BD, like so. And what we have set out to prove is that the angle which this cutting straight line makes with the tangent straight line, each angle here will equal its angle in the alternate segment. What this means is that the angle DBF will equal the angle in this segment, right? Because we have the angle on this side of the cutting straight line, so its alternate segment will be on the other side of the cutting straight line. And similarly, for the angle EBD will equal the angle in this segment here, DCB. This is what we have set out to prove. We begin by drawing the straight line BA perpendicular to EF at the point B. Do this by proposition 111. And we join these straight lines AD, DC, and CB. This is all just simple postulate 1. Now, because BA has been drawn perpendicular to a tangent straight line from the point of contact, we know that the center of the circle ABCD must lie somewhere on this straight line AB. That's proposition 319. And so if the center lies somewhere on this straight line AB, we can say that this straight line AB is a diameter of the circle ABCD, which means it cuts the circle into two semicircles. We have semicircles on either side of AB. Now, because this segment ADB, which the straight line AB cuts off, is a semicircle, because AB is a diameter, we know by proposition 331 that the angle in it must be a right angle. And so we can say that this angle ADB right here is a right angle because it's in the semicircle ADB. Again, that's proposition 331, Thales' theorem. And so if we look at the whole triangle ABD, we know by proposition 132 that if we add the three interior angles of any triangle together, they must add up to two right angles. Now, looking at this triangle ABD, one of the angles in it, namely the angle ADB, simply is a right angle, which means by common notion 3 that the remaining angles BAD and ABD must add up to another right angle so that the whole can equal two right angles. Okay, so the angle BAD plus the angle ABD equals a right angle. Now we also know that the angle ABF is a right angle because we constructed AB such that it makes right angles with EF, so the angle ABF is a right angle, which means by common notion 1 that the angle ABF equals the angle BAD plus the angle ABD, right? Because both of these are equal to a right angle. One of them is a right angle and the other two add up to a right angle, same thing. Okay, so the angle ABF equals the angle BAD plus the angle ABD, which means if we subtract the angle ABD from both sides, what we're left with is if we look at this whole angle ABF and we subtract the angle ABD from it, the remaining angle that we're left with is the angle DBF. And so we can say that the angle DBF is equal to the angle BAD. It's common notion 3. Now, we know that the angle is DBF plus the angle DBE. These two angles have to add up to two right angles. That's proposition 113. And we know by another proposition, 322, that if we look at the cyclic quadrilateral BCDA, so that whole thing right there, we know that its opposite angles must also add up to two right angles. And so we can say that the angle BAD plus the angle BCD, also equal to right angles. So common notion 1 tells us that the angle DBF plus the angle DBE equals the angle BAD plus the angle BCD. Now, we know that the angle DBF is equal to the angle BAD, which means that the remaining angles, namely angles DBE and angle BCD, these two angles must be equal again by common notion 3. And so we can say that the angle DBE is equal to the angle BCD. Now we have actually accomplished what we set out to prove. We set out to prove that the angle which the cutting straight line makes with the tangent straight line at the point of tangency, each angle made there will equal the angle in its alternate segment, and we have just shown this. So if we look at the angle DBF, its alternate segment is the segment BAD right here. And the angle in the segment BAD is the angle BAD, and we've just shown that the angle DBF is equal to the angle BAD, like so. And we have also shown that the angle DBE is equal to the angle DCB. And these being the angles in the alternate segments, we have done what we set out to prove, which means we're done with the proposition, therefore, etc., QED. Another very important proposition at the tail end of book 3. It certainly takes some practice to get used to being able to recognize what exactly is an alternate segment and what angle in it is equal to what other angle. It's a little bit difficult to figure out when you're first getting used to it, but I do recommend that you get this down so that you know it quite quickly, because it will come up very often. Other than that, I have nothing to say about this proposition, so I shall simply move on to proposition 3.33.